Hey guys, Mr. Strange here. Let's talk about elastic potential energy. So we're talking about springs and rubber bands, anything that can bend and bounce back. But in order to understand that, we need to talk a little bit about Hooke's law, and then we'll use that to determine the amount of work done, which is the energy, and that gets us into elastic potential. Won't take very long. There's not much to it. Most of this is in the notes. I'll be doing a couple different examples here. So if you look at the notes, you'll see some other examples. Basically, Hooke's law. So Hooke he was a scientist back. He was a contemporary of Newton. Um, I think I pulled up some pictures. So there you go. There he is. He's an old dead white guy, like most of the people that we study. But anyway, so there he is. If you look at more images, though, it's some of these people are not Hooke. That's Newton. That's Galileo. So anyway, be careful when you Google stuff. Regardless, Hooke's law. So say we had a spring attached to a wall. So here's a great spring. And say I was going to stretch or compress this. So we'll do both. So I'll draw another one here. And say this one, we stretched it out. Yeah, I know, they're bad springs. You try drawing them. All right, so, and this one will be compressed. When the spring is in its natural state, this little line right here, so we'll draw it all the way down. This is called the equilibrium point. So this is where its natural state, equilibrium. And this will normally define to be our zero, because we're going to measure the displacement. And so when I stretch it from equilibrium, the amount of stretch that I give it, this would be my x. This would be the amount of stretch or compression. So it's the distance away from the equilibrium. Since I compressed it, this would be negative x in this direction. And then if you think about it, if I have to pull the spring this way, then the force that the spring is exerting on me, so the force here that's way too thick. The force of the spring is in this direction. So it's trying to pull me back. If I'm pulling this way, the spring pulls back. So we end up getting a negative force of the spring on whatever the object is. Likewise, down here, if I push it, the spring is going to push back this way. So the force of the spring here would be in this direction. And what we'll get is we always get a negative force that's applied. So the displacement's this way, the force is pushing back. And Hooke's law just says that that the amount of force, and also you need to understand that the force that it takes, that's required to stretch this or compress it, it varies. So the more you compress it, the harder it gets, the more force. So if you go further, the force would actually increase. Either way, if you stretch it, it gets harder as you pull it. So the further away from the equilibrium you are, the more force that's required and the more force that the spring pushes on you. So Hooke's law, and that's Hooke with a K, is relatively easy mathematically. And all it says is that the force of a spring on an object is equal to negative kx. And this k, this is called the spring constant. The units on the spring constant are going to be Newton per meter. So Newton per meter. And this is just a measure of how stiff the spring is, how hard it is to stretch or compress. So the higher the K value, the more force that's required. And then X is just the displacement from equilibrium. So it's how far have we moved it in the positive or negative direction, the displacement. That's Hooke's law. Now, if we flip this, so if I don't want the spring on the object, what I want is the object on the spring. So if I wanted the force of the object on the spring, so on the spring, I would just flip that. So that would just be kx. So we're going to use this next to get quantify elastic potential energy. So what we need to do is we need to think about the work done. So let's say that let's say that I have a spring that's been compressed some distance. So say I had like a block that was sitting there and it compressed it. So the equilibrium point, this would be my 0. And let's say it compressed it, so we measure to right here. This would be negative x. So we've compressed it some distance here, from 0 to negative x. In that case, the force of the spring on the object would be just negative kx. We know that. So that's Hooke's law. Now, if I want to determine the amount of energy or work that the spring does on the object, so the work of the spring on the object would be the force times the displacement. But the force changes. It's not a constant force. So I don't want to just use this. I need to use this divided by 2. So we take the final and the initial and we'll divide by 2. So what I get is I get that the work is going to be the force, which is negative kx, divided by 2. And that's going to be times the displacement. But the displacement was negative x. So now simplifying this a little bit, the negatives, and I'll pull out the 1/2. So I get 1/2 of kx times x. And so the work done is going to be 1/2 kx squared. So this is the amount of work done by the spring on the object. Therefore, this would be my change in energy as well. And that change in energy is creating elastic potential energy. So my equation for elastic potential energy will be 1/2 kx squared, where k is the spring constant, x is the displacement of the spring from equilibrium. And that's it. Very similar to kinetic, although this is potential, not kinetic. So we're not talking about movement. It's once it's stopped. So now we'll do a couple examples. And again, there's more examples in the notes. So a 5 kilogram block is hung from a suspended string and pulled down until it stretches the spring 0.75 meters. So what we have is it's hanging. You know, let me change this color. So we have a spring, connected to a block. And the block is pulled down. So the total displacement from equilibrium, wherever that is 0.75 meters. We have the spring constant, so that's going to be my K. I have 5 kilograms. And all I want to know is what's the elastic potential energy. So for this one, my elastic potential energy is going to be 1/2 of K times x squared. So we just substitute the values. 1/2 of 130 times 0.75 squared. You do that calculation and you get 36.56 joules of energy are stored in the spring. And if I release it, it would then shoot up and turn it all into kinetic energy. Yeah. All right. Let's look at another one. Suppose you load a 0.09 kilogram arrow into a bow and pull the bowstring back 0.40 meters. The bow has a spring constant, 900 Newton per meter. We want to know the speed as it leaves the bow, and then we'll determine how high the arrow goes if you shot it straight in the air. So essentially we just have a bow and we're going to pull it backwards and shoot an arrow. So this bow, when it bows like this is what's producing the elastic energy. So what we want to know is, we'll just start with our work energy principal is equal to the final. And the first thing we're going to do is the arrow speed. So the total energy before plus any work is equal to the total energy final. So to begin with, when I pull it back, all that I have is elastic potential. I don't have any kinetic. The gravitational don't care about, because it's going to be right when it leaves it. So we don't really care about the y direction. There's no work done on it. It's already pulled back. And when it's done, all of that is going to be transferred into kinetic energy. And now we just, we put it we put our equations in, we mathematize it. This one's going to be 1/2 k x squared is equal to kinetic energy, which is 1/2 mv squared. So you can see they're very similar, but very different. So please don't confuse them. We're trying to solve for v. So first I see that I have 1/2 on both sides. So if I divide by 1/2, I'll get 1. And so to get v, let's divide by m. So I get k x squared divided by m equals v squared. To get rid of the square, I take the square root. And now we just put in our numbers. Our k is 900. Let me do this. So v is equal to the square root of 900 times x. So it was displaced 0.4 squared divided by the mass, 0.09. You calculate that, get a velocity of 40 meters per second. So that's your velocity as it leaves. All right, now let's think, okay, so what if we just shot it straight in the air? Now you already have well, we didn't actually determine it, but anyway, I'm going to walk through the entire process again because I really want you guys to just kind of follow this process all the time with these types of problems. So the total energy initial plus any work equals the total energy final. And in this case, what we're doing is we're actually shooting the arrow straight up into the air. So we're going to load it up with elastic potential. It's going to go up and stop and then come right back down while you run out of the way. But what we care about is the energy right here at the top. So first, to begin with, we have elastic potential. There's no work done. And at the end, we'll just have gravitational potential. So now we substitute our equations, 1/2. See, I did it. I start confusing it with the kinetic. So I get 1/2 k x squared is equal to the gravitational potential is mgh. So if I want to solve for the height, I divide by mg. So I get 1/2 k x squared divided by mg is equal to the height. We put in all our numbers there and we'll get a height of 81.63 meters. Yeah, pretty straightforward. Let's see. So this will be the last example. A 4.3 kilogram block is sliding across a frictionless surface at 2.3 meters per second when it hits an elastic bumper. The block compresses the bumper 0.4 meters. What is the spring constant of the bumper? Again, you approach all these problems the same. We don't care what they're asking for. We can just solve for it. So we have a frictionless surface. We have a block that's sliding across it. So we have a velocity 2.3, and it's gonna hit a bumper. So there's a wall here, maybe with a spring, and then some kind of stopper thing. It's maybe like that. So it's gonna slide across, strike the bumper, and then compress it 0.4 meters. And we're gonna want to find K of that spring. That's a 4. All right, so let's think about it. So my total energy initial plus any work done is equal to my total energy afterwards. So the energy that I have to begin with is all kinetic. So I have kinetic energy plus the work. Oops, I'm sorry, there's no work done in this. If I had some friction or something, maybe I'd throw it in there, but so equal to. Now when it compresses and stops, that's gonna all be stored in elastic potential. Now we change. So mv squared equals, it's an equals. Whenever I write close, it always connects them. It's pretty annoying. 1/2 k x squared. We're trying to solve for k. We want the spring constant. So I see I have 1/2, so I can divide that off both sides. So you get mv squared equals k x squared, and then divide the x squared. So you get mv squared divided by x squared is equal to your spring constant. Your mass is 4.3, your velocity is 2.3, your compression is 0.4 squared. You put in all those numbers, and we get a spring constant of 142.169 Newton meters. And that's it. Just a few examples. But there's not much to it. It's just knowing the formula. By the way, all of these formulas are on the equation sheet. So looking at the equation sheet, so again, I'm on the equation side. But if we look here, let's see, there's a momentum, change in momentum, that's impulse. Like here's kinetic energy. And so you can remember that. Let's look at big K. Big K is kinetic energy. So there's your kinetic energy equation. Then we go down. There's our definition of work and energy. P, that's going to be power. We haven't talked about that yet. So let's keep going down. You got to come all the way down here. This is where you get your potential. U is potential, if you look it up. So there's your equation. Go over here. There's your potential, gravitational potential. It's change in, but it works the same. Change in Y is just your height. Anyway, that's it. Have fun.